Welcome back everybody to another video lecture. This is video 2 in our thermochemistry series. So in this video we're going to be talking more about calorimetry and about how to set up our thermodynamic equations, as well as a new concept called enthalpy. So as I mentioned, our specific objectives describe how calorimeters are used to measure heat flow. We're going to be doing a little lab where we use calorimeters in class. We're going to construct those thermochemical equations and solve for enthalpy changes in chemical reactions by using heats of reaction. Calorimetry is a way that we can measure the heat into or out of a system during our chemical processes, and this is based on the fact that heat released has to be absorbed from somewhere, it has to be absorbed someplace else, and so shockingly the device that we use to measure this absorption or release of heat is called a calorimeter, or as we'll see in class, a styrofoam cup. So as I mentioned, that we'll be using foam cups in class. These are excellent heat insulators and are commonly used as simple calorimeters under constant pressure. And if you think about this, styrofoam cups really hold a lot of heat in, and that's why hot drinks such as hot cocoa or coffee are generally sold in those styrofoam cups, or before it was environmentally friendly, not friendly to do so. They really do hold that heat in there. There's this term here of a Dewars flask, and the idea for this thing is it's just a metal container that's also seriously insulated. I like to think of this more like a thermos, like those thermoses that maybe like you'll see like people who are working the night shift drink out of, because those are also super insulated. So now this is probably the most important thing on this slide, is this concept of enthalpy. It's a hard concept for some people to memorize or to understand, so really try to wrap your brain around it. Okay, so it says for systems at constant pressure, the heat content is the same as a property called enthalpy of the system. So if we're looking at the heat content, we're really looking at the enthalpy. Here is a picture of what a calorimeter with the foam cups would look like. I'm not sure if you can see this, but there's actually two cups nested here together. So there's this one down here, and then there's this one up here. And this is, again, just providing a little bit better insulation. So normally we'll go ahead and we'll cover this cup, maybe even with another cup. You can see that the thermometer is here, and then we have this little stirrer that we put in there. So on this slide, we're going to talk a little bit about the variables that we might see in the equations when we're making our calculations. So if we see this delta H, this stands for the changes in enthalpy. So remember, this delta here is just changes in the enthalpy. So changes in the heat content. Well, we already saw a variable for heat, that was Q. So in this textbook or in our lectures, we can use Q and delta H kind of interchangeably. So we had this equation that we saw in the last video, MC delta T equals Q. So now we can just, since these two are equal to each other, we can also say that our change in enthalpy is going to be measured by this equation as well. So we need to look at our delta H values. So remember, we had talked about that if we had a negative Q value, we were going to be exothermic. So of course, if we're having if these two things are equal to each other, a negative delta H is going to give us an exothermic, or indicate that it's an exothermic reaction, and a positive delta H will indicate that it's an endothermic reaction. And if you think about this, if we're talking about heat content, if we're adding more heat content, of course it's going to be a positive number. If we're losing heat content, it'll be negative. In the last video, we talked a little bit about calories and then the calorie difference that you see like on a package of food. So one way that they can actually measure how many calories with a big C or a little c is to use this thing called a bomb calorimeter, and it's used by nutritionists to measure the energy content of food. So there's much more fancy and sophisticated calorimeters that we can use than the ones that we'll be using in class. So here's a picture of a bomb calorimeter. You can see that it has many of the same characteristics as the styrofoam calorimeter that we're going to be using in class. Notice it has two layers, but now we've got a steel layer here and an insulating layer. We still do have a stirrer and a thermometer. That really hasn't changed, and we're still having some water inside. So it's similar, but this is just a much more fancy and expensive version. Here is an example problem showing how we can calculate the enthalpy change in a calorimeter experiment. So go ahead and read this. It says when 25 milliliters of water containing 0.02 moles of hydrochloric acid is that 25 degrees Celsius is added to 25 milliliters of water containing 0.025 moles of sodium hydroxide at 25 degrees. In a foam cup calorimeter, a reaction occurs. Calculate the enthalpy change in kilojoules during the reaction if the highest temperature observed is 32 degrees Celsius. Assume the densities of the solution are 1.00 grams per milliliter, and that's because that's the same density as water, and your concentration of acid and base here are really small. So remember, we're going to be using our equation, Q equals MC delta T. So we go ahead and put our knowns in. So we know that water has a specific heat capacity of 4.18 joules divided by grams times Celsius. We look at the total volume, and so we've got 25 plus 25, so that's giving us 50. Here's our initial temperature, 25. Here's our final temperature of 32. And so the unknown that we're looking for is that delta H value, and we're looking for that in kilojoules. Now here is the tough part for kids to figure out. The big thing here is if you look here, you're going to see that it's negative delta Q of the surroundings. So remember, we can't actually measure what's happening in the system. We can only measure the heat change of the surroundings. So whatever the change is going to be in the surroundings, it's going to be the opposite inside the system. And so that's why we're using a negative delta Q here, okay? And so that means that we're going to have a negative in front of our equation here. So we go ahead and we plug in our values because we know that we are looking for... Oh, my bad. It looks like we need to find those that mass first. And so the way that we're going to do this is we're going to take the mass, we're going to take our 50 milliliters. We know that it is 1 gram per milliliter if we look at that density, and we're going to find that we've got 50 grams of our solution. And so now we're going to calculate our delta T. We're going to take our final minus our initial, so that's what we're doing. So we're coming up here with, it looks like 7 degrees Celsius. I just moved the slide up a little bit so we could see it a little better. So now we can go ahead and we can plug in our values here. And so you can see our delta, oops, my bad, our delta H here. So we've got our negative mass, and it's not that it's actually a negative mass. Remember that our Q of our surroundings has to be negative, so that's why we're plugging the negative in here. MC delta T, plug those values in, plug and chug, and we're coming out with negative 1.5 kilojoules. So because we came up with a negative delta H value, we can say that this reaction is exothermic. So one of the things that you guys definitely are going to need to be able to do is to look at a graph and to determine, is this going to be an endothermic or an exothermic reaction. So if we're looking here at this picture, we can see here are reactants, carbon and oxygen. Over the process of the reaction, if we look at the energy, like this is the energy level where these reactants are, but through the course of the reaction, our products are at a lower energy than what the reactants were. So here's our carbon dioxide way down here. So we can see that 395 kilojoules of energy was given off. Again, if we're having energy given off, then we're going to know that it is an exothermic reaction. So another way besides looking at the graph that we can tell if it's an exothermic reaction is, remember, we always say exothermic's releasing energy, so we can see that energy is in the product side here of our chemical reaction, and so that's the clue that it's going to be an exothermic reaction by looking at the chemical equation. So just as a review, exothermic reactions, the products are in a lower energy than the reactants, and we saw that on the graph, thus energy is released. So in this picture, or in that last graph, we had a delta H of negative 395 kilojoules. So the negative sign does not mean that there's negative energy, but it just means that energy is lost. So this is actually like a really super duper important thing. You guys might want to just kind of try to wrap your brain around this one too. So it's not that we're having negative energy, it just means that heat or energy is being lost. So let's look at this graph and see what's going on. So if we start down here at the bottom, we look at the reactants. So the reactants are at a low energy. You look at the products. Hopefully you guys are like, it's a decomposition reaction. Yes, yes, it is. So we have this decomposition reaction and our products are at a higher energy. So in order to decompose, we needed to add heat to this. So you guys might remember we talked about adding that little triangle sign a lot with our decomposition reactions because we're adding heat. So 176 kilojoules of energy is going to be absorbed. So if energy is being absorbed by the system, remember that's why we would call it an endothermic reaction, because energy is going into the system. As we talked about on the last graph, a clue by looking at the chemical equation is now let's look where our energy or heat was put into this equation. So we can see that it's a reactant now. So if you're having to add heat to a reaction, it's going to be if you're adding heat, it's going to be on the reactant side. Again, a clue that it's going to be an endothermic reaction. So as a review, for endothermic reactions, the products are higher in energy than the reactants. Energy is being absorbed. From that graph, we saw that 176 kilojoules, in fact, were being absorbed, and that the positive sign means that the energy is being absorbed. Okay, now is time for the fun stuff, our thermochemical equations. So an important idea here to remember is that chemistry happens in moles. We spent a lot of this year working with moles. So when we look at a chemical equation, we have those coefficients. Remember that those coefficients were representing moles. So if I was to read this equation right here, we would say that we have 1 mole of methane plus 2 moles of oxygen yields 1 mole of carbon dioxide and 2 moles of water. And the additional thing here is this energy that's being added to the end here. So an equation that includes energy is called a thermochemical equation. So what we want to learn here from this, or what we can tell, is that 1 mole of methane releases 800.2 kilojoules of energy. And then when you make 802.2 kilojoules of energy, you're also making 2 moles of water. So there's just some ways to think about this. So for every 1 mole of methane you use or burn, you are producing 802.2 kilojoules of energy. So one of the things that you're going to see in doing your problems and reading your textbook is that the heat of reaction is the heat change for an equation exactly as written. When we do these thermochemical equations, we always need to include the states because the change in heat will be different for different states. Now there's this thing called standard conditions. It is different from STP. I guess this is why we have that different number on the back of our periodic table. So notice that your pressure is the same as at STP, but at STP it's at 0 degrees Celsius, so at standard conditions we call this 25 degrees. So now we're going to get into some problems, and you probably will be doing a worksheet like this in class, so make sure that you're paying attention to how to solve these problems. So here's that equation that we saw on just one of the previous slides. Here's our methane, here's our oxygen, producing our carbon dioxide and water, and our 802.2 kilojoules. So the problem is, if we have 10.3 grams of methane, they're burned completely, how much heat will be produced? Well, remember one of the things we talked about last time was that if we have 1 mole of methane, it's going to give off 802.2 kilojoules. Notice, though, that they're giving this to us in grams. So, of course, we're going to have to do a gram to mole conversion. So if we look here, we start with our known value, of course. We're going to go ahead and convert it into moles. But then remember, for every mole, it was producing 802 kilojoules. And so but this is obviously more than, it's actually a little less than 1 mole. So then when we do the math on this, we're going to see that our value is a little less than our 802.2 kilojoules. So our delta H for this reaction is negative 514 kilojoules, which means the heat is released for this reaction. And you might be like, well, where did you get this negative? Well, if you look over here, remember how we talked about that if your energy is on the product side, you're going to have an exothermic reaction, which means your delta H has to be negative. So the summary so far really has to do with this idea of enthalpy. So remember that enthalpy is the heat content of a substance at a given temperature and pressure, and it can't be measured directly because there's no set starting point. The reactants start with the heat content, the products end with the heat content, so we can measure how much this enthalpy is changing over time. Also, you need to know that the symbol for enthalpy is this H. The change in enthalpy is the delta H. Heat is released. The heat content of the products is lower. That means your delta H is going to be negative, so that's going to be an exothermic reaction. If heat's being absorbed, the heat contents of the products will be higher, and your delta H will be positive, meaning that it's an endothermic reaction. So looking at this graph, we can see that our reactants are at a high our products are at a low energy state, and then so our delta H here, our change in energy, is going to be less than 0, so we're going to have an exothermic reaction. Remember we said if delta H was negative, which would be less than 0, it would be exothermic. So for this one, we can see that we have our reactants and our products. We're increasing here, so our delta H is going to be greater than 0, so we know that's an endothermic reaction. And our delta H is going to have a positive value, which it would be if it was greater than 0. Guys, I hope this video was helpful. Remember to go back and maybe write down some questions that you have that you want to answer in class. Make sure that you're seeing me during class, before or after school, to help answer this. This is one of the more tricky chapters and concepts to understand, but hopefully we'll get enough practice in class. I'll see you there. Bye.